Ever wondered what's lurking beneath the surface of a moon made of ice?
Well, today we're taking a deep dive into that.
Yeah, we're diving deep into the world of tidal love numbers to try and find out.
They're like cosmic fingerprints
Ooh, like that.
for icy worlds like Europa and Titan.
Those mysterious moons, that might just be hiding, well, massive hidden oceans. It's so cool.
You're exactly right.
Yeah.
These love numbers are a bit of a secret weapon, scientifically speaking.
Okay.
They help us decipher these messages these moons are sending us.
Messages.
Yeah, through subtle wobbles in their gravity fields.
It's like they're trying to whisper to us from billions of miles away.
Exactly.
So break it down for us. What exactly are these love numbers? And what makes them so special for learning about what's under all that ice?
Okay, so imagine squeezing a rubber ball.
Ugh.
It changes shape.
Right.
Tidal love numbers work in a similar way.
Okay.
But instead of your hand, it's the immense gravitational pull of a giant planet.
Like Jupiter.
Like Jupiter or Saturn tugging on these moons.
Okay.
And the numbers tell us how much the moon stretches and squishes, which, believe it or not, reveals what's hiding beneath all that ice.
Okay, let's unpack this. We're talking about measuring how much a moon deforms under the gravitational pull of its planet.
Mm-hmm.
How can you possibly measure something like that from millions, even billions of miles away?
It's incredible, right? We're talking about sensing changes in a moon's gravity field.
Okay.
So subtle that it's like detecting the height difference of a coin lying on Earth from space.
Wow.
The key to these measurements, spacecraft.
Ah, okay.
They can pick up on these tiny wobbles as they orbit these moons.
That's mind-blowingly precise.
Yeah.
Now, in our deep dive today, we're focusing specifically on Europa, which orbits Jupiter, and Titan, a moon of Saturn.
Mm-hmm.
And, we've all heard those exciting whispers about the potential for vast oceans hidden under their icy shells.
Mm.
How can scientists be sure there's really something down there?
The subtle wobbles we mentioned.
Yeah.
They hold the key. By analyzing how the gravity field changes as the spacecraft orbits the moon, we're essentially peering beneath the surface. And what we're finding is that these variations point to the existence of something less dense than rock or ice, something more like a global ocean.
So it's like these moons are sending us a coded message in the form of gravity.
Yes.
And scientists are cracking the code to see what's hidden beneath the surface.
Precisely. And the really cool part is that even though Europa and Titan both seem to have these hidden oceans, they're incredibly different worlds.
That's right. The paper we're looking at actually highlights these differences really well.
Yeah.
It points out that Europa has a higher density, which hints at a composition with more rock, maybe even a metallic core. On the other hand, Titan seems to be made up mostly of ice and water. That's a pretty stark contrast.
Absolutely. And these differences in composition are super important when we start to think about the potential habitability of these oceans. What are they made of? What's the chemistry like? Are there conditions that could support life? Those questions are directly tied to what these moons are made of and how their interiors are structured.
This is where my brain starts to hurt a little. I get the whole gravity thing, but the paper talks about treating the moon's crust, which is super thick, like tens of kilometers, as a membrane.
Right.
It's like saying an eggshell is basically the same as the whole Earth.
Yeah.
How does that even work?
Think of it as a clever trick scientists use to make the math a bit easier to handle. It's called the membrane approximation.
Okay.
Imagine trying to calculate every single detail of how that massive icy crust bends and flexes.
Yeah.
It would be a nightmare.
Yeah.
So instead, they treat it like a thin, flexible membrane. The amazing thing is, this actually works pretty well.
Yeah.
Even though the crust is thin compared to the entire moon, its properties are still super important for understanding what's happening underneath.
So it's like you don't need to analyze every ingredient in a cake to know if it's going to be dense and fudgy or light and airy, right?
Exactly.
You can kind of get a sense of how it's going to behave just by looking at it.
Exactly, and that's what those effective parameters mentioned in the paper are all about. They're like shortcuts that capture the big picture of the crust's behavior without getting bogged down in the nitty-gritty details.
So by figuring out these parameters, we can actually learn something about what's going on under the surface, even if we can't see it directly. What kind of things are we hoping to find?
For starters, we're trying to figure out just how deep these oceans go. Are they shallow seas?
Okay.
Or vast planet-wide bodies of water?
These parameters help us answer that.
And even more excitingly, we can start to understand the interaction between the ocean and the icy shell above. Is there a chance that material from the ocean is being pushed up to the surface? Could there be plumes of water erupting from the ocean and spewing out into space?
Whoa. That's incredible. So these parameters aren't just about numbers. They're about potentially unlocking the secrets of entire alien oceans.
You've got it. And when we start looking at those oceans, one of the biggest questions we have is, what are they made of? That's where the density of the ocean comes into play, and it's a key piece of the puzzle we're trying to solve with these tidal love numbers.
Okay, so we're talking about the density of these hidden oceans. Why is that such a big deal for understanding these moons?
Well, imagine you have two oceans, both the same size.
Yeah.
But one is full of, say, super salty water, and the other is more like a giant freshwater lake.
Okay.
That difference in density would have a huge impact on how those oceans behave, right?
Yeah, that makes sense. Denser things tend to be heavier, more sluggish.
Exactly. And it's the same with these moons. A denser ocean means it's less likely to be pushed around by the gravitational pull of its planet. It's like trying to stir a thick milkshake versus a glass of water.
Right.
The milkshake takes more effort, right?
So a denser ocean would mean smaller, less dramatic tides.
You got it. And that's what makes these love numbers so useful. By measuring the extent to which the moon deforms, essentially how big its tides are,
Right.
we can start to get a handle on the density of that hidden ocean.
So the more the moon stretches and squishes, the less dense the ocean, and vice versa.
Precisely. But here's where things get even more interesting. The paper also talks about something called the screening effect, which adds another layer of complexity.
Okay, hold on. We talked about screening earlier, but that was about the core and the mantle, right? How does it work with the ocean?
It's a similar concept, but instead of the core masking the mantle, we're talking about a potential layer within the ocean itself, throwing us for a loop. Imagine a scenario where the lower part of the ocean, closer to the moon's core, is denser than the upper part.
Okay.
This denser layer could actually dampen the gravitational pull from the planet, making the moon appear more flexible than it really is.
It's like having a heavy weight at the bottom of a pool.
Yes,
It might make the surface look calmer, even if there's a lot of movement going on underneath.
that's a great analogy. So even if a moon seems to be stretching a lot under the planet's pull, we can't immediately assume it has a low-density ocean. There might be this hidden, denser layer messing with our measurements. It's like the moon is playing a cosmic game of hide-and-seek.
This is blowing my mind. So these tidal love numbers aren't just telling us about the size and shape of these moons. They're giving us clues about the layers within them,
Yes,
even the ones we can't see.
exactly. It's like we're using gravity to peel back the layers of these moons, like an onion, trying to understand their hidden structures.
Speaking of hidden structures, the paper goes pretty deep into the nitty-gritty of how scientists model these moons, especially when it comes to the deep interior. There's a lot of talk about fluid crust models. What's that all about?
That's a really clever technique scientists use to isolate the effects of the deep interior on the love numbers. Remember, these moons aren't just simple balls of rock or ice. They have layers, each with its own density and properties.
Right, like the core, the mantle, the ocean, and then the crust on top.
Exactly. And each of those layers interacts with the others, making it tricky to figure out what's causing what. So imagine for a moment that you could magically replace the entire crust of a moon with a fluid of a specific density.
Okay, so we're talking about a hypothetical scenario here.
Right.
Not something that's actually happening.
Right. This is the thought experiment, a way for scientists to play with the variables.
Okay.
By replacing the crust with a fluid, they can create a simplified model that lets them study how the core and mantle alone respond to tidal forces.
It's like creating a controlled environment where they can isolate the effects of just the core and mantle, without the crust getting in the way.
Precisely. And by comparing the results from these fluid crust models to the actual love numbers we measure, they can start to piece together the real-life properties of the core and mantle. Are they dense and rigid, or more fluid and flexible?
So these models help paint a more complete picture of what's going on deep down inside these moons. What have we learned about Europa's interior from these models?
One of the big questions surrounding Europa is whether its core is solid or liquid.
Okay.
And while we don't have a definitive answer yet, these models suggest that even if the core is liquid, it's likely very dense and behaves almost like a solid when it comes to tidal forces.
So even if there's a giant molten sea of metal at Europa's core, it's not going to make the whole moon wobble around like a water balloon.
Not quite. It's more about the overall density and rigidity of the entire core mantle system. And that's where the concept of an equivalent shear modulus comes in handy.
Here we go with the technical terms again. Break it down for us.
Essentially, it's a way to describe the rigidity of the core and mantle as if they were a single combined unit.
Okay.
Instead of getting bogged down in the details of each layer, we can treat them as one and talk about their overall resistance to deformation.
So it's like saying, okay, we don't know exactly what kind of cake this is, but based on how it's holding its shape, we know it's got to be pretty dense and fudgy, not
Exactly.
light and fluffy.
And this kind of simplification is incredibly useful for understanding how these complex systems work.
This is all fascinating stuff, but so far, we've been talking about tides as if they're this static thing.
Yeah.
But the paper mentions dynamical tides, which sounds way more intense.
Mm-hmm.
What's the difference? So we've talked about static tides, but then the paper mentions dynamical tides.
Yeah,
Which sounds way more intense.
it is, a little bit.
What's the difference?
When we talk about static tides, we're simplifying things a bit. We're picturing the moon and its ocean kind of just hanging out there, holding still.
Yeah.
But in reality, everything's in motion.
Right.
Dynamical tides take that motion into account. And that's where things get really interesting.
Okay, so it's like a more realistic way of looking at how these tidal forces actually work in a universe where nothing sits still.
Exactly. And because we're dealing with motion, we also have to consider this fascinating phenomenon of resonance.
Resonance. Now, doesn't that have something to do with those videos of opera singers shattering glass with their voice? What does that have to do with tides?
You're exactly right. It's the same principle.
Wow.
Just like a wine glass has a specific frequency at which it vibrates, so too do these moons and their oceans.
Okay.
And when the tidal forces from the planet hit that sweet spot, that resonant frequency, things can get amplified.
Whoa, so you're saying depending on how deep Europa's ocean is, the tides could be way more powerful than we initially thought. What kind of effects are we talking about here?
You're catching on quickly. The depth of the ocean is crucial here. A shallower ocean is far more likely to experience these resonance effects. And when those tides get amplified, they can actually have a really profound impact on the moon's interior. We're talking about the potential for increased geological activity, perhaps even influencing the evolution of the moon itself over time.
Now we're talking. So it's not just a case of the tides going up and down a bit more. These amplified tides could be driving volcanic eruptions, triggering ice geysers, even causing tectonic shifts within that icy shell, all because of this cosmic dance between gravity and resonance.
Precisely. It totally changes our perspective on these seemingly frozen, desolate worlds. We used to think of them as static and unchanging, but now we're realizing they could be incredibly active environments, all thanks to these dynamic forces.
It's incredible to think that something as seemingly simple as the depth of an ocean could have such a dramatic impact on the entire moon. And you mentioned that the paper actually calculates those resonance frequencies for Europa and Titan. That must be some seriously complex math.
It is, but the key takeaway is that these calculations give us a range of ocean depths that are most likely to produce these amplified tides. It's like having a treasure map guiding us towards the most exciting places to look for activity.
Wow. So if we find an icy moon with a relatively thin ocean, we might expect to see some pretty spectacular stuff happening on its surface.
That's incredible. We've covered so much ground in this deep dive. From those initial, almost poetic hints in the moon's gravity to these mind-blowing revelations about hidden oceans, internal structures, and dynamic tidal forces that could be shaping entire worlds. It's been amazing.
What's the one big takeaway you want our listeners to walk away with?
I think the biggest takeaway is that these tidal love numbers, as complex as they might seem, are more than just abstract calculations. They're giving us a glimpse into worlds vastly different from our own, hinting at the possibility of hidden oceans and the potential for life beyond Earth.
It's like unlocking a secret code, revealing the hidden language of the cosmos, one love number at a time. What an incredible journey this has been. We've explored the cutting edge of planetary science, delving into the mysteries of these icy worlds and unraveling the intricate ways that gravity shapes the universe around us. Thank you so much for joining us on this deep dive. Until next time, keep those questions coming and never stop exploring.